One of the things we've been doing with derivatives is talking about them as a rate of change of various quantities. In today's section, we're going to ask the question of what happens if we have multiple quantities that are changing over time, but those quantities are related to each other in some fashion. Can we get some idea about how their rates of change are related to each other? An example of this that I've always liked thinking about is the idea of blowing up a balloon. Say we have some balloon. Just going to draw just kind of a circle there, but it's going to be a three-dimensional thing. We have some sphere, and we're blowing air into it at some consistent rate. Essentially, what we're doing by doing that is increasing the volume of the balloon. And we want to talk about what is this? How does the size of the balloon really change if we do that? For instance, if there's not much air in the balloon already, and we're blowing it up, it's going to actually expand quite rapidly. But if we already have a lot of air in the balloon, and we put the same amount of air into it, it's not going to expand quite as much. That expansion slows down a bunch. So the rates of change of the volume versus the size of the balloon, in some sense, are related to each other, but somehow the rates are not related in a very simple fashion, necessarily. The book actually has this balloon problem as problem 9. Here we are going to make the assumption that the balloon is a sphere, because in order to be able to quantify this relationship between the volume and the size of the balloon, we're going to have some formula for the volume. We sometimes have to make those kind of simplifications if we're going to be able to even tackle these kind of problems. But in problem 9, they ask, a spherical balloon is inflated with gas at a rate of 10 cubic feet per minute. So we've got gas going in. At 10 cubic feet per minute. Then they ask, how fast is the radius of the balloon changing at the instant the radius is, well, they have part A is 1 foot and part B is 2 feet. We'll get to why there's different parts there in a moment. But first we need to talk about what exactly is going on. So here, because we are dealing with a spherical balloon, we have to use a formula for volume from geometry. Maybe not, don't remember this formula, but the volume of a sphere is related to its radius by 4/3, so 3, pi r cubed. In this problem, we know that the volume, the V, is increasing at a rate of 10 cubic feet per minute. In other words, we could write that as dV dt is 10 cubic feet per minute. Notice here that we are not differentiating this with respect to r. This is the derivative with respect to time. The volume changes over time. It does change based off of r, but we're given information about it changing over time. But how can we incorporate this rate of change, this derivative, into our formula? Well, since it is a derivative, the rate of change is a derivative, what we could try to do is differentiate this formula. Essentially do the implicit differentiation we're doing in the last section. But this time we have to keep in mind that v and r are not being treated as independent variables. Neither one of them are. We're not differentiating with respect to r. We're differentiating with respect to time, this other variable t. So both volume and radius have to be treated as functions of t, even though t doesn't actually appear in this formula right away. So we're going to differentiate both sides of this with respect to t. course, here on this side it's pretty easy. The derivative of v with respect to time is just the derivative of v with respect to time. On this side, the 4/3 pi, that's a constant, so we can pull it out. But now we need to differentiate the r cubed. Here we're going to have to go ahead and use our general power rule. Remember that power of 3 comes down. We reduce the power of 3 down to a 2, so we have an r squared. But then we also need to multiply by the derivative of the inside, the dr dt. So that's being multiplied in there. Of course, we can then go ahead and simplify this a little bit. The 3 down here can cancel with that 3 there. So we have 4 pi r squared, but also multiplied by dr dt. So now we have a new formula. We have a formula for the derivative of v related to the derivative of r. These rates of change are now related to each other. You may have noticed, however, that we do actually have the radius itself still in the formula, that we do have an r still in the formula. This frequently happens in these kind of problems, where the original variables may not go away. In fact, we could have had a v in here as well if v hadn't been by itself. So what that actually means in this particular problem is that the rate of change of the radius, because the rate of change of the volume is staying the same, the rate of change of the radius is going to be dependent on how big the radius already is. And we already even mentioned that. We mentioned that our intuition was that when the balloon is small, it expands quickly, and when the balloon is big, it expands slower. Those rates of change depend on how big the balloon already is. This formula has just put some mathematics to that intuition. So in order to actually solve the problem, we're going to remember there's two parts. We had how fast is the radius of the balloon changing at the instant the radius is 1 foot? So if r is 1 foot, what is dr dt? That's what they're asking here. Of course, we already have dv dt is equal to 10 cubic feet per minute. So we'll go ahead and just plug those in here. dv dt is 10. I'm going to leave off the units for the moment. We have a 4 pi. We have a 1 squared. But then we still have dr dt. And if we go ahead and solve for dr dt, essentially just take 10 divided by 4 pi. The 1 just goes away, of course. 10 divided by 4 pi. Go ahead and use a calculator for this. And I'm rounding it to 2 decimal places. I get 0.78 feet per minute. Of course, here, keep in mind I'm using the units that we're dealing with. So everything was in feet and minutes before. So we have feet per minute. In part B, they're asking the exact same question, but now they're saying the radius is 2 feet. But I'm doing the exact same thing. Instead of putting a 1 in here, I'm going to put a 2. So we still have 10 because we still have the same rate of change of the volume. So 10 equals 4 pi 2 squared dr dt. We're still basically taking 10 divided by 4 pi, but then we also divide it by another 4. And we get, after some rounding, 0.20 feet per minute. It's like 0.197 or something like that. But if you round it to the nearest 2 decimal places, it's 0.2. So this gives us the idea that the bigger the balloon already is, the slower that radius is expanding. This is an example of a problem that we call related rates. And the book gives us basically a breakdown of the steps that we need to go through in order to solve a related rates problem. So the first thing you need to do is identify what quantities are either given to us or that we have to actually determine in the actual problem. And this also requires you to think about what rates what sorry, not what rates, what quantities are actually changing over time. What quantities actually have a rate of change to even talk about. If something is constant, it might be important in the problem in setting up a relationship, but we will not need to actually differentiate it when the time comes to do that step, because it will be a constant in that case. So we need to identify what kind of quantities we have, and in step 2, we're going to have to find some way to relate them to each other. If it's a more geometrical problem, maybe a real world example where we have dealing with distances and things like that, it can be helpful to draw a picture. I mean that's frequently the case in word problems. Is pictures are pretty useful. In step 2, we need to write some equation that relates all the variables whose rates of change are either given or determined, or to be determined. So we basically have to take all that we know about the quantities and the situation that we're in, and boil that down to usually a single equation that we can work with. If there's any extra variables in there that we don't really care about or we don't know any information about, we'll need to figure out some way of getting rid of those. Find maybe there's some other equations that will allow us to substitute those out. Finally, once we actually do have an equation that relates the quantities that we want to talk about, we differentiate both sides. We basically use implicit differentiation to differentiate both sides of our equation with respect to time. Finally, we need to put in all the values that we know about our variables. So in our previous example, we had to use the fact that we knew that the derivative of volume with respect to time was 10, and then we had to plug in the values of the radius. Keep in mind here that we need to, when we do step 4, we absolutely must do that after we differentiate. Because if variables are changing over time, if we plug in the values before we differentiate, we're treating those values as if they're constant, that they don't change over time. We're telling the problem that we're dealing with a constant value, in which case we're telling the problem that we're in a completely different situation. We need to be able to deal with these values changing over time, and not just the values as they are in the particular instant that we're talking about. We throw everything off if we do that. Let's actually work problems, though. This will be a lot more clear when we go through some problems. So it's supposed to be problem 13. Problem 13. This is actually a more business problem, an economics problem. The revenue R from selling X units of a product is given by R equals 1200X minus X squared. The sales are increasing at a rate of 23 units per day. Find the rate of change of the revenue when A, X equals 300 units, and B, X equals 450 units. Let's follow the 4-step process that the book has given us. So, step 1, we need to identify any quantities that we're talking about. What do we have that is changing? What is relevant to our problem? Well, I mean, they basically spell that out for us in the very beginning of the statement. They're talking about the revenue R, and the fact that we're selling X units of some product. They don't actually tell us what product we're selling. Both these two things are changing over time. There's not really a picture we can draw here, unfortunately. Step 2, what is the relationship between our variables? What is the relationship between R and X? they actually give that one to us as well. We're not in a situation where we need to derive that. So, but they told us that the revenue is given by 1200x minus x squared. That's our relationship. Most of the time in these related rates problems, step 2 is the longest. But sometimes if they actually just give us the equation, it can actually be a rather short problem. Step 3, we need to implicitly differentiate this equation, r equals 1200x minus x squared, by differentiating both sides with respect to time. Of course, the derivative of r with respect to time is just the derivative that we want. On this side, we're going to have to differentiate each term separately. The 1200 just kind of comes along for the ride. We're differentiating x with respect to time. Here, we're going to have to use our general power rule, but x squared becomes a 2x, but then we also need to multiply by the derivative of x, the derivative of the inside. Step 4, now we're going to need to plug in our values. So we're given information about the problem. We're actually told that the sales are increasing at a rate of 23 units per day. We have to interpret what that means. So we're talking about units per day, so we're talking about x changing. We're saying that the rate of change of x is 23 units per day. So basically, on one day we're selling so many, and the next day we're selling 23 more. And then the next day after that, we're selling 23 more than we were doing the second day, and so on and so forth. But we're given two problems, two sub-problems, you could say. Part A, they actually tell us that x is 300 units. And they're asking us, find the rate of change of the revenue. What is dr dt? So dr dt, if we already know that dx dt is 23 and x is 300, we just put those values into our equation. We have 1200 times dx dt, which is 23, minus 2 times x, which is 300, times dx dt, which is 23. Again, go ahead and use a calculator for this. It comes out to be 13,800. Now, what are the units on this? Well, we're talking about revenue changing over time. I'm assuming here that the revenue is in dollars. I mean, technically, they didn't tell us what the currency was, but we'll just assume dollars here. And of course, over time, we're using the same unit for time here. So we're talking about $13,800 per day. That's how much our revenue changes over time. So if we already have 300 units, and the next day we're going to have 323 units, then this is essentially estimating that our revenue is going to increase from what we already have by 13,800. We're going to have that much more revenue the following day. Part B, they're changing x to 450 units. But the way we solve the problem is exactly the same. We already have our formula for dr dt in terms of x and dx dt. So we're just basically changing what x value we plug in. We still have the 23s, but now the 300 is going to be 450. So we have a 1200 times 23 minus 2 times 450 times 23. Again, just going to use a calculator for this. We get 6,900 with the same units. Those are dollars per day. So that means if we're already selling 450 units, and the next day we're going to sell 473 units, then we expect our revenue to actually increase by $6,900. Now that is a smaller increase, but keep in mind we are increasing. We're selling more units, so we probably have a higher revenue already. So we have one revenue that's increasing by a lot, but when we get more units, we're increasing it by smaller amounts, but it's still increasing. Moving on, let's work on problem 17. In problem 17, we have a boat that's pulled by a wrench on a dock, and the wrench is 12 feet above the deck of the boat, but the boat is pulled by a winch on a dock, and the winch is 12 feet above the deck of the boat. The winch pulls the rope at a rate of 4 feet per second. Find the speed of the boat when 13 feet of rope is out. So they actually give us a picture of this. Unfortunately, I wasn't able to get a really high quality version of that picture to put in here. But at least we have kind of an idea what's going on. We've got this boat in the water. The winch is way up here, 12 feet off the water. Oops. But the boat's being pulled by that winch. So we want to set this up. We want to first identify our quantities. What quantities are we dealing with? Maybe we'll even draw a better picture. So I can actually put in some values. So we have the winch up here. We have the boat down here. The bottom of the dock is down here, but the dock is really kind of all over this place. So we want to identify all the distances that we have. We have the fact that the boat is a certain distance from the bottom of the dock. I'm going to go ahead and call that R. I'm going to call this one X. We also have the length of the rope. There's a rope going from the winch to the boat. I'm going to call that length R. Just R for rope. Finally, we have another distance. We have the height that the winch is above the water. Say that's 12 feet. We don't actually need to give a variable to this because that distance is not changing. I mean, if you want to give it a value of it, you could, but when we get to differentiating things, we don't want to have extra variables that we have to differentiate that aren't changing anyways. So we have x equals distance from boat to dock. We have R is the length of the rope. Of course, when we're actually dealing with this stuff, we need to think about what the derivatives of these actually are. What are the rates of change of these? The rate of change of the rope. Well, that's just how much is the rope changing over time. In this particular case, we actually do have a value for how much that rope is changing. We're pulling the rope in at a rate of 4 feet per minute. 4 feet per second. 4 feet per second. Of course, that when we're doing that, the rope is getting shorter. So we're not really saying that it's increasing by 4 feet per second, where it's decreasing. We need to put a minus sign here to denote that. dx dt, this is what the rate of change of the distance between the boat and the dock is. So basically that's telling us how fast is the boat moving. This is, you could say, the speed of the boat. Now, what is the relationship? So this is part 2. Find the relationship between our quantities. How are R and X related to each other? Here we're going to have to use a little bit of geometry. We have a triangle here. In fact, assuming that the dock is actually vertical here. We kind of have to assume that. I don't think they really. I mean, I guess technically here they're saying that this is 12 feet higher than the deck of the deck of the boat. So whether or not this dock is really actually vertical, we're saying that this height is still 12 feet. So we can still think of this as a right triangle, and we can use the Pythagorean theorem. Pythagorean theorem says that if we square the legs of a right triangle, this x and the 12, add them together, we get the square of the hypotenuse, the r. So you can say 12 squared plus x squared is equal to r squared. Or I can go ahead and replace 12 squared with 144. Okay, a little bit more room to work on it. We move on to step 3. We differentiate this equation with respect to time. Of course, when we differentiate 144, that is just a constant. It turns into a 0. When we differentiate x squared and r squared, we have to use our general power rule, or the chain rule, however you want to look at it. The x squared becomes a 2x times the derivative of x. And the r squared becomes a 2r times the derivative of r. Step 4, we're going to plug in our values. Remember, we had dr dt is equal to negative 4 feet per second. And they also give us the information that because we want to find the speed of the boat when 13 feet of rope is out. So we know that r is equal to 13 feet. We want the speed of the boat. That means we're looking for dx dt. Unfortunately, we have another value in our formula. We have an x. We still have an x in there. And we're not given information about what that x is supposed to be. Well, how do we get it? Well, remember, x is still related to r through our original Pythagorean theorem equation. If we know the value of r that at the time that we're looking at, we should also be able to find the value of x using this formula. Basically, I'm going to go ahead and put in 13 feet into my formula, and I'm going to solve for x. Now, remember, I'm only doing this to find the x at the time that we're talking about. I'm not doing this before I differentiate. We have to distinguish between those two cases. There's a time and place to be able to plug in values in order to derive the other values that we're working with. Don't do it before you differentiate. We go ahead and solve. We have x squared is equal to 13 squared, which is 169, minus 144. That comes out to be a 25, which means that x is equal to 5. Of course, we throw out the negative 5 solution. That's not really relevant when we're talking about distances like we are. But now we can go ahead and use the values of dr dt, r, and 5 and plug them into our formula. So we have 2 times 5 times dx dt is equal to 2 times 13 times negative 4. So dx dt is equal to, well, what we have here, 2 times 13 times negative 4 is negative 104. Obviously, 2 times 5 is 10, so we're dividing out by 10. So we get a negative 10.4. And the units here is a distance over time, so it's feet per second. And that we could see as our answer. We might want to think about what the negative here means. That negative means that this distance from the boat to the dock is getting smaller. It's decreasing. We're getting closer and closer to the dock as the rope is getting shorter and shorter. So at the time when that rope is 13 feet long and we're we're actually 5 feet from the dock. We're moving towards the dock at 10.4 feet per second, assuming we're on the boat. Alright, one last problem for this section. We're going to look at problem 25. In problem 25, this is another economics problem. The profit for a product is increasing at a rate of $5,600 per week. The demand and cost functions for the product are given by P equals 6,000 minus 25x, and C equals 2,400x plus 5,200, where x is the number of units produced per week. Find the rate of change of the sales with respect to time when the weekly sales are x equals 44 units. Okay, before we really get into all the different equations and stuff, we do want to follow our 4-step process. The first thing we want to do is identify what we're even talking about. What are the quantities that are changing that we need to talk about? Of course, the first thing that we want to talk about is x equals the number of units. That's already kind of in the problem already. And then we have various things that do depend on x. For instance, they gave us some formula for P. P here is our price. They also gave us a cost function. So we have a C. And of course, they started off with the profit increasing at a certain rate. So we do want to talk about P equals profit. Even though it's not expressly referenced in the problem, we should also include revenue. Because obviously when we're dealing with profits and costs, the revenue is kind of in there already. Part 2, we want to find some relationship between the quantities. Well, they give us a rate of change for the profit. They tell us that the profit is increasing at a rate of $5,600 per week. So our formula, whatever relationship we have, is going to have to involve the profit. But they want us to find the rate of change of the sales. They're basically asking us how many more or less units are we selling to get that change in profit. So somehow we essentially want some relationship between the profit P and the units X. These other quantities, these that are changing over time, are probably going to have to come into play in some form or fashion, but eventually we only want to have P and X in our equation. So, let's start with the profit. What is a formula for profit? We have to remember these relationships between these various quantities. Profit is revenue minus costs. So we're basically starting with P, but then we're getting into R and C. We need to replace the R and C with expressions in terms of X. C is actually pretty easy. They actually give us a cost function. They'd say the demand and cost functions for the product are given by blah, and C equals 2,400x plus 5,200. So we have a fixed cost of 5,200 and a variable cost of 2,400. Revenue is a little bit more complicated because we have to recall that the formula for revenue is units times the price. And here's where the price comes into play. They give us the demand function, the demand formula for P. They tell us that P equals 6,000 minus 25x. So for this relates the price to however many units are sold at that price. Of course, when we go ahead and set P equal to that, we basically get to plug that into this equation. And just to make it easier on us, I'm going to go ahead and distribute the x to both terms. So we have a 6,000x minus 25x squared. if we put these values of R and C together for P, we get P is equal to 6000x minus 25x squared minus 2400x plus 5200. Putting them in parentheses here because I do need to remember to distribute this negative. So I have a 6000x, but I also have a minus 2400x. If we go ahead and combine those, we get 3600x. We still have the minus 25 squared, or 25x squared. There's no other terms to combine that with. And then here's our constant term. We need to remember that negative. So finally, that should be here. This is our relationship. So, like I said before, part 2 can actually be kind of the longest part of this, depending on how well we know this relationship already. Now that we have a relationship between profit P and units X, we're going to go ahead and differentiate it. Just do implicit differentiation. We have the derivative of P with respect to time. On this side, we differentiate each term separately. We have the 3600 comes along for the ride. The X we differentiate to get the dx dt. For this term, we do need to go ahead and use our general power rule. We still have the minus 25, but that's going to be multiplied by 2x and to the derivative of x. Finally, the minus 5200, that actually becomes 0. That doesn't play into our derivative. So you might think, well, why did I have to remember to distribute the negative? Well, we want to be actually correct in our formula, even though it didn't actually play a role in the derivative. Alright, now we're going to plug in our values. And these are the values that we're going to take from the problem that I really haven't even bothered to write down yet, because this is the first point where they're relevant. We are given the rate of change of the profit. We're told that the profit for the product is increasing at a rate of $5,600 per week. And then we're asked to find the rate of change of sales, so we're looking for dx/dt with respect to time when the weekly sales are x equals 44 units. So when we have this set of data, what is dx/dt? Essentially, we're in a situation where we know we've sold 44 units, at least at a particular time, but we're seeing our profit change over time, and we want to know how many more units or how many fewer units are being sold. Well, we just go ahead and plug in their values, replace the dp dt by 5600. That's going to equal 3600 dx dt. We don't have a value for that yet. I'm going to go ahead and combine the 25 and the 2, so just a minus 50 times x, which is 44. And then we still have the dx dt. $50 times 44 is actually 2200. 3600 minus 2200 is 1400. So we have 5600 equals 1400 times dx dt. If we divide it out by 1400, we can actually get rid of the hundreds parts. So it's really 56 divided by 14, and that actually gives us a whole unit of 4. 4 units per week. So when we already are selling 44 units, but we're seeing our profit increase by 5,600 per week, that means we should expect to sell 4 more units the next week. Alright, so hopefully by this point you got an idea of what the process is, our four-step process here, and how all that works together in order to be able to talk about these related rates. Of course, this is the last section of this chapter, so we're going to have our first exam coming up in the next week, or this week, depending on when you watch this video, before we move on to chapter 3 in the next week. So I'll see you guys at the exam.